Hello class. In this video we're going to finish up our module on the introduction to statistics, and today we're going to talk about different types of variables. All right. So first and foremost, what is a variable? Simply, it's just something that varies. It's an observation that can vary. And you guys have talked about variables for a long period of time. So for instance, when you took math classes, specifically things like algebra, and you have like y and x that can take on a wide range of variables or a wide range of values in math class, these are variables. Y and x are the variables in the math equation. Whereas 5 in this particular math equation, 5 is always going to be the exact same thing. 5 is a constant in this math equation. So we can have constants and we can have variables in math. We can have constants and variables in science as well. So there are many different ways of labeling variables. There's many different names of variables, and we can there's 3 naming conventions for variables that I'm going to talk about in this class. Okay, 3 different naming conventions for variables that are going to tell us some important information about those variables, the statistics that we can conduct with those variables. So what statistics can we conduct? What statistics can we not conduct? If we conduct this particular statistics, perhaps it's a useless thing to do. We were not going to get any important information out of it. What kind of manipulations to the variables that we can do? Can we add a number to it? Can we subtract a number to it? Does that even make any sense? So having some knowledge about the variable and the kinds of variables that we're interested in will tell us a lot about which statistics we can and cannot use. It also is going to tell us something a little bit about the research design. Okay, so there's going to be a lot of important information that we can glean by knowing what kind of variables we are looking at. All right, so 3 different naming conventions we're going to use for variables. Function, things like independent variable versus dependent variable. We've already talked about that. You've used these terms many times before. The distinction between discrete and continuous variables. This is important. It lets us know what the best way of displaying the variable is, what kind of graph we should use, what kind of frequency distribution we need to look at to gain a sense of a graphical representation of that variable. And the last one is the scale of measurement. All right, the scale of measurement is going to help us figure out what statistic we need to use when trying to summarize this variable. Perhaps which measure of central tendency we need to use. Do we look at the mode? Do we look at the median? Do we look at the mean? That is going to, which scale of measurement a variable has is going to help us pick out which measure of central tendency we should use. All right, so variables by function. Many of these we've already talked about before. The independent variable. An independent variable is a variable that we manipulate when we are in an experiment. The dependent variable, this is the variable that we measure, and we're looking at changes in the dependent variable as a function of the independent variable. Control variables, I don't think we mentioned this in this class, but there's many things that we want to hold constant throughout an experiment to make sure that any changes in the dependent variable are a function of changes in the independent variable. And lastly, but not least, confounding variables. So these are variables that might affect the outcome of the dependent variable that we are not manipulating, all right, that we have not accounted for, okay, or we're unable to control. So we call these either confounding variables, extraneous variables, sometimes nuisance variables. So let me give you an experiment, and we'll talk about what the independent variable and dependent variable is for this experiment. So here we're looking at different reaction times in the Stroop task. The Stroop task is a famous task in psychology, and it's one of those tasks, probably the only task that I know of, that you'll see across every single discipline within psychology. You see it in cognitive psychology, you see it in personality, you see it in abnormal psychology, you see it in developmental psychology, you see this thing all over the place. So it's a very important task that's ubiquitous to all of psychology. So how does the strip task work? For the strip task, you see a word, and that word is a certain color. All right, so for instance, it might be green, blue, yellow, and your job is to say the color of the word, but not the word itself. Now, for some trials of this task, it's very simple. All right, for this control condition, it's very easy because the words are not colors themselves. All right, but the strip task changes this up. So we might have some compatible trials. Here we see that all of the colors, all right, all the colors, the word is actually saying the color itself. So we're supposed to say red, but the word says red as well. We're supposed to say yellow, but the word is yellow. So in this case, we're actually going to be faster in many instances than in the control condition. All right, because they match up. Reading is something that's pretty automatic. So we are quicker at identifying the color as red because it says red. All right, and our third category of trials here, these are incompatible or incongruent trials. Here we're supposed to say the color, but the word reads as a different color. So here we're supposed to say yellow, green, blue, red, green, yellow, blue, red, green, yellow. It's harder to do this because reading is automatic. We want to say what the word actually says. So we can look at many different things. We can measure someone's attentional capabilities. We can look at developmental disorders. We can look at the effects of aging. We can look at the effects of particular mental disorders. Did I say that? I might have said that twice. All right. If I did, I apologize. We can look at many different things with the Stroop task. So the independent variable here is the condition. Are we going to put our subjects in the control condition? Are they in the compatible condition or congruent condition? Or are they in the incompatible or incongruent condition? Now let's say subjects do one of each of these lists. All right. Sometimes the subject might get compatible first, then control, then incompatible, and other times a different subject might get incompatible, then control, then compatible. And we might counterbalance the order. Remember that word, counterbalance, to control for these order effects. So first of all, is this a between subjects or a within subjects manipulation? This is within subjects because all subjects get all three levels of the condition. Again, what's the independent variable? The independent variable is the trial type: control, compatible, incompatible. What's the dependent variable? The dependent variable is the reaction time. Maybe it's the reaction time to complete the entire list. All right, so independent variable, it's the condition. We're manipulating that between or within subjects. My apologies, it's within subjects. But we could do a between subjects manipulation if we wanted to. Subjects would either get compatible, or they would get incompatible, or they would get control. They would not receive all three. That would be between subjects. Just as a little bit of review for you guys. The dependent variable might be the average response time, or it might be accuracy. We see that subjects for the incompatible trials, they're more likely to be inaccurate as well. So we could look at reaction time or response time, and we could look at accuracy. Control variables, all right, there's some things that we want to make sure are consistent throughout the experiment. So maybe the lighting in the room, all right, it's harder to see color if it's dark. Maybe we want to make sure that there's the same number of items per list, or otherwise it might take someone slower for a list because there's more items on the list. So that might be a dumb example, but there's plenty of things in an experiment that we want to make constant, and we want to make sure that do not vary across the experiment, or otherwise we're unable to tell if changes in the dependent variable are caused by our manipulation of the independent variable. Think for a second, what are some confounding variables? What are some confounding variables that we might not be able to control that might lead to differences in how people perform? Maybe something like if our subjects are colorblind. Steve Smith in the psychology department at Dahlonega. He has color blindness, so he would not do very well at this task. That's a confounding variable that we would have to try to account for in some reason. Another thing, how about whether or not English is your first language, or if you're fluent in English? All right, if I were to switch these up and instead of writing these in English, I wrote them in German or Japanese, and you were not fluent in those languages, this task would be very easy, and you wouldn't do any different between the compatible and the incompatible trials, because you don't know what color words refer to which color. You don't know the language. So people might differ in their proficiency in English, and the more proficient you are in the language, the greater the Stroop effect is going to be. And here I'm defining Stroop effect as the difference in reaction time between the congruent and the incongruent trials. All right, so color blindness, knowledge of English. How about tiredness? Some students might have taken caffeine beforehand. Taking caffeine like it's a illicit drug, might have drank coffee beforehand, something like that. Maybe they haven't slept in a couple of days. That might lead to some confounds in this study as well. All right, things that might impact the dependent measure that is not just the independent variable. All right, so here are some examples of those different variable types that are important for experiments. All right, so we've talked about those before, but what do we call variables if we're doing correlational or differential research? Let's say that we're looking at a correlation between two things. Let's say we're looking at the relationship between intelligence and job performance. All right, intelligence and job performance. Notice here, and this is going to be important later, I have a double-headed arrow. Double-headed arrow does mean that we're looking at a correlation between two variables. So in this situation, we might call both of these dependent measures, right? Or dependent variables. We have the dependent variable of intelligence. We have the dependent variable of job performance. All right, so we call both of them dependent variables if we're doing correlational research, specifically when we just care if there's a relationship at all. But sometimes in differential research, we are interested in prediction. We're using one variable to predict the outcome of another variable. So perhaps, and especially if we're interested in hiring somebody for a job, we might be interested in using intelligence to predict how well that person is going to do at this job. Notice how the arrow has changed. It has gone from a double-headed arrow indicating a correlation to a single-headed arrow representing prediction here. All right, we're using intelligence to predict job performance. Here we're going to change the name of our variables a little bit. We're going to call our variable that we're using to predict our outcome the predictor variable. Intelligence here is our predictor variable for job performance. And job performance, the thing that we're looking to predict, is our criterion variable, sometimes called outcome variable. You'll see people use outcome variable and criterion variable interchangeably in the literature. So when we start to use prediction, we are going to start calling things predictor variables and outcome/criterion variables. When we do this, we're interested in a branch of statistics. I don't say branch. Branch makes it sound like it's like completely unique. We're looking at a specific statistic called regression. All right, regression is all about prediction. And there's many different types of regression out there. We're going to talk about a single form of regression later on in this class, but you can do a lot of fun things with it. In fact, let's say that we're interested in something like predicting who's going to succeed in school, or maybe who's going to succeed in graduate school. That might be more appropriate for you guys because you've already gotten into college. So how do graduate schools make their predictions? Okay, who do they decide to hire? They use this technique called regression, and they have multiple predictors to see who they think is going to succeed college the most. And they have some kind of cutoff, and if you, based off of all of these different predictors, you have a good prediction of succeeding and graduate school, they accept you into the program, otherwise they do not. So we might have multiple predictor variables. We might have something like your GRE score, your GPA, whether or not you had an internship or not, maybe the quality of your internship. So with differential psychology, we might have multiple predictors for a single outcome. Okay. Moving on. That's stuff you've probably gotten before. Now let's make a distinction between discrete variables and continuous variables. Discrete variables are variables that can take on only a limited number of values. All right, only a limited number of values. There are only so many values that the variable can take on. All right, maybe something like, what do I want to say? How many children you have? That's a good one. You can have 0 children. You can have 1 child. You can have 2 children. You can't have 1.5 children. Okay, that does not work out. You either have the child or you don't have the child. So you can't have 1.25 children. All right, these are variables that typically take on only whole numbers. All right, there's no fractions of something. So how many children you have, maybe how many letters in your name. Okay, I have 5 letters in my name, my first name. I don't have 4.5 letters. Okay, there are only so many values that letters in your name can take on. It can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It can't be 9.25. All right, how many students are in the classroom? Again, it can only be a whole number. It can't be half a number. Now, it might be the case that someone's asleep, and we might want to say it's something like 6.5 students in the classroom, but they're still a person. Okay, you can only have whole numbers here. Another good example here for a discrete variable: which experimental condition are you in? Are you in the experimental condition? Are you in the control condition? Maybe it is a experimental condition that has multiple levels to it. So maybe you're in this condition, this condition, this condition, or this condition. You can only be in one of those 4 conditions. There isn't an infinite number of potential experimental conditions that you could be in. All right, we design our study with a limited number of conditions that the person can be in. All right, so this is a discrete variable. Discrete, there's only a limited number of values that the variable can take on. An independent variable for a study is always going to be discrete. Okay, it's always going to be discrete. The independent variable can only take on a certain number of values because you can't run infinite numbers of experimental conditions. Something that's important for us to note, and it's going to be important for us later on, a term that I've used is level. When we talk about a independent variable, it has different levels to it. Now, it might just be 2. It might be you're in the experimental condition or you're in the control condition. All right, but it could be something else. So for instance, when we talked about the strip task a little while ago, there were 3 levels of the experimental manipulation: the control block, the compatible or congruent trial block, and the incompatible incongruent trial block. So there were 3 levels to the independent variable. Okay, you'll see the terms condition, level, and sometimes group used interchangeably, but it's important that we get this term early on because it's going to be important later. How about from the last lecture when we talked about our experiment where people are trying to take a test, and in the experimental group there is a band playing, and the other group there is not a band playing. All right, so you're assigned to either the experimental group or you're assigned to the control group. Okay, there are 2 levels to this independent variable, and the way that I described it, it's a between subjects manipulation. You're in either this group or you're in that group. Okay, again, try to do some testing of your memory, some review. That was the word I was looking for. How about if we're interested in something like, do video games cause aggression in human beings? So maybe we have a experiment where we get people to participate in 1 hour of playing a video game, and then we have some measure of aggression. And let's say we either have them play no video games, so this might be our control group. We get them to play a very passive game, maybe something like Animal Crossing. Not a ton of violence in Animal Crossing. We get them to play a video game with some cartoon violence, maybe Mario Kart. And then more realistic violence with Grand Theft Auto. All right, and then we measure their aggression. This is an independent variable that has 4 levels. Okay, control, Animal Crossing, Mario Kart, Grand Theft Auto. Okay, discrete variables can only take on a limited number of values. Our independent variable can have different levels to it. Levels are the number of different conditions there are. All right, we can contrast discrete variables with continuous variables. Continuous variables are variables that can take on the full range of values, a potentially unlimited number of potential values. So let's say something like the temperature within the room. I mean, sure, we might say that it's 68 degrees Fahrenheit, 69, 70, 71, and those are whole numbers. But we could try to measure it more accurately, and we might have fractions of a degree. How about if we're looking at the speed in which someone completes a task? Okay, sure, it might be 1 second or 2 seconds, which are whole numbers, but if we become more accurate, we might be able to get down to milliseconds. All right, so there are an infinite number of values that a continuous variable could take on. Here's a good way of looking at it. Discrete, we have instances only for the whole numbers. Continuous, we could have something in between those whole numbers. All right, how tall are you in inches? Okay, now, even though somebody might say, I was trying to think about how many inches convert, let's say 70 inches is how tall a person is. Maybe 2 people are 70 inches tall, but we could do a more fine-grained analysis to find that one person is 70.5 inches tall and the other person's 70.25 inches tall. And we can get more and more accurate as we go further and further down there. Okay, reaction time in a Stroop task. Sure, it might be something like 2 seconds, but we could get down to the millisecond. So there are a vast number of values that the variable could take on. Okay, how many milliliters of cortisol, the stress hormone, is in your blood? All right, we could do that. Break that down into more and more fine-grained unit of analysis. How many pounds of food do you eat during a meal? All right, we're not just, I mean, how much food you eat, we could do in discrete categories, or we could do it as a continuous variable. So let's say it is the hot dog eating competition that happens Independence Day. I think it's Independence Day that they do that. Have you guys seen that? It's disgusting. Okay, they're doing it in discrete units. How many hot dogs do you eat, period? So then you can't really have fractions. But you could do it in pounds, okay, the weight of the food. And in that regard, we're looking at a continuous variable. All right, it might be 5.678 pounds. All right, typically our dependent variable is going to be continuous for our research studies. This is not always the case. So for instance, the number of items that you answered correctly, that is a discrete variable, right? You can't get like half an item wrong. Well, I guess it depends on how the task is set up, but that's pretty much a discrete variable. But many times our dependent variable is going to be continuous. All right, let's do a little bit of review. So I'm going to tell you something, and I'm going to ask you if it's discrete or continuous. Heart rate, discrete or continuous. This is a continuous variable. Okay, we can get beats per minute, but we could break it down and get a little bit more fine-tuned than that. The number of romantic relationships in your life. Sure, you might think that Frank should only count as a quarter of a relationship, but you know, you can't really do that. Okay, number of romantic relationships in your life. This is a discrete variable. How about the color of your car? Now this one is interesting, and it's I said it because I wanted to get a little bit to show you it's one of the conundrums of trying to break something down as to only discrete or only continuous. Now we might say the color of your car is discrete. So it's either going to be green, black, white, red, all the different colors, okay? There's only a limited number of colors that we have words for. But we could say color in terms of the wavelength of light. And in this regard, it would be continuous. So we could treat color as both a discrete variable or a continuous variable, all right? But most of the time, there's only a limited number of colors. It's not like you see very many colors that are fuchsia or chartreuse for a car. All right. So it depends on how we measure the color. The last way that we can divide variables are the scales of measurement. All right, the scale of measurement for a variable. Now, this is a naming convention that was developed by S.S. Stevens, a very important individual in the history of psychology. In fact, I think in around 2000, they did the most influential psychologist of the 20th century, and old S.S. Stevens was something around the 50th position. If you take a course in sensation and perception, you're going to learn a lot about S.S. Stevens. One sec. Sorry about that. I had to blow my nose, and nobody wanted to see that. Okay, so the scales of measurement are arranged in such a way that as we move on to the next scale of measurement, the variable tells us more information. We start off with a level of measurement that the variable does not give us that much information about the thing that it describes. But as we go up in scale of measurement, we're gaining more and more information from that variable. All right, so the scale of measurement is going to help us in determining which statistics we should use to analyze the variable, how we can manipulate our data, okay, how we can interpret our data as well. All right, so the first level of measurement at the bottom that's going to tell us the least amount of information is a nominal variable. It's the nominal scale of measurement. Sometimes this is called a categorical variable. All right, categorical, nominal, same thing. You can use those interchangeably. These are variables that they tell us category placement, but they don't tell us anything about ordering of the variables. We can't tell which variable or which outcome, which value of the variable is better than another one. So how about something like the sex of a person? Okay, so let's just say for the sake of this argument that we have two sexes. We have male and we have female. All right, which one of those is better? Now you probably have an idea in your mind, right? You might have some prejudices or something like that, like, oh, my sex is the best, but not one of them is better. There's no mathematical reason why one should be above the other one. How about eye color, right? Again, you might have some preference for a particular eye color, but mathematically, there's no reason why brown eyes should be better than hazel eyes, should be better than blue eyes, and so forth. All right. So we might use a nominal variable for the placement into particular categories. And we might use numbers to assign these particular categories. So let's say that I say blue eyes are 1, brown eyes are 2, gray eyes are 3, green eyes are 4. Does that mean that green eyes are twice as good as brown eyes? No, that doesn't make any sense, right? Are brown eyes better than blue eyes? No. We just use the numbers to denote category distinctions, that they're separable from one another. We're not doing it in terms of one's better than the other. All right. Maybe pet owned, yes or no. That's another example of, well, it's a distinction between the two of them, but there's not an ordering to it. Most of the time when we're doing an experimental condition, these are just differences in the experimental condition. There's not an ordering to them, right? So think about a couple slides ago where we had the no contact control group where they didn't play video games, Mario Kart, Animal Crossing, Grand Theft Auto. Is one of these video games better than the other one? No, I mean, we might rank them in some way, but we're just using this variable to denote a category distinction, not any differences in which one is better or not. Okay, how about basketball jersey number? All right, we have LeBron. He has the number 23. Okay, and we have James Harden, the beard, and his number is 13. Does this mean that LeBron is necessarily better than Harden? No, the number does not indicate that. Does this mean that LeBron is 10 points better than Harden? No, it's not. I mean, you could think of the same thing with football jersey numbers. We're using the numbers to denote differences in people, that the 23 is LeBron, that we are able to see that when we watch a basketball game. We're not using these numbers to denote that someone is better than another person. All right, now let's think about it this way. Let's say that two basketball teams are playing against one another. Let's add up the numbers on both the teams and take an average of those. And then we can tell which team is better by taking the average of their players' numbers. Does that make any sense? No, it does not, because the numbers only tell us differences. This person is different than this other person. It doesn't have anything to do with basketball skill or anything else. Nominal variables tell you category distinctions, but they don't tell you rankings in any way. Nominal variables give you the least amount of information for a variable. It's the scale of measurement that gives us the least amount of information. All right. Experimental condition here. We have, again, our stripped example, the control condition, the congruent condition, the incongruent condition. If we were to assign numbers to these conditions, maybe 1, 2, and 3, these numbers just tell us category distinctions. They don't tell us anything about which condition is better than another condition or on any ranking metric whatsoever. We move up from nominal, and we go to ordinal. Ordinal variables tell us ranking. All right. We can tell from the numbers in an ordinal scale of measurement which one is better in some way. You can tell a ranking of the variable in some way. So let's say something like high school class rankings. If you're first in your class, we know that in terms of GPA, you have done the best. We don't know by how much, though. And that's the important thing here with ordinal variables. We know rankings, but we don't know the interval between individuals. And in fact, the interval might be inconsistent. So maybe you rank your favorite bands, okay? You have something like the Beastie Boys at number 1, and then you have Slipknot as number 2, and you have System of a Down as number 3. You don't know with that ranking if the Beastie Boys and Slipknot are very close to one another in being that person's favorite band, or if there's a huge distinction between those two. You don't know if the difference between Slipknot and System of a Down is very close, or if it's pretty massive difference between those two. You don't know if I just give you a ranking of favorites in a person's mind, how close are they ranked. So socioeconomic status, if we did this in terms of poor, middle class, or rich individuals, we don't know if the interval between poor and middle is the same extent between middle class and rich. And in fact, the poor and the middle class are closer together in terms of how much money they make compared to middle class and rich. So the interval is not consistent, or doesn't necessarily have to be consistent for an ordinal scale of measurement. Let me give you a good example of this. So here we have people running a marathon. And after the marathon, we see that this person is in first place, this person is in second place, and this person is in third place. It could be the case that the person finished in first, and then 25 seconds passed, and then the person came in second, and then 25 seconds later happened, and then the person came in third place. That could be the case. It could not be the case. Right? We don't know if these intervals are consistent. It could be the case that it was a photo finish and the first and second place were very, very close to one another. But the third place person, it took them quite a while to cross the finish line. We don't know just by the ordinal scale of measurement what the intervals are. All right. So let's say I were to ask you to rank the rap groups Migos, Public Enemy, and Wu-Tang Clan. Okay. And if you were to do that and you said Wu-Tang Clan was in first, because obviously, then Public Enemy, and then Migos, you don't know how close these are to one another. So perhaps if I were to rank them, I'd put Wu-Tang and Public Enemy fairly similar to one another. They're both really good rap groups. And then I put Migos way behind. But again, you don't know if I had ranked Migos somewhat closer to Public Enemy, right? That I thought that they were fairly equivalent rap groups. All right, you just don't know when we have an ordinal scale of measurement. You can just tell which one is the best, which one's in the worst, which one's in the middle. You don't know if the intervals are consistent in an ordinal scale of measurement. So we have lots of nominal variables in psychology. We have a lot of ordinal variables in psychology, a ton of ordinal variables. One good example of this, come on, computer, there we go. A great example of this is a Likert type scale. Okay, Likert. It's not Likert. If you say Likert, I get mad. It's not. Likert said his name Likert, so that's what we're going to call it. Likert items, like on a scale of 1 to 6, how much do you agree with this following statement about your personality? I enjoy long hikes on the beach. Long hikes on the beach. Long walks on the beach. There we go. So if you were to say something like that on a scale of 1 to 6, we do not know if you pick a 6, how different in your mind psychologically that is from a 5. We don't know in your mind how different a 5 is from a 4. Now, clearly in your mind, a 6 is greater than a 5, but we don't know if the intervals between all of these are consistent with one another. And that's going to be important because the way that we're going to interpret the data from a Likert item type scale, it's going to be important. We can't just take things like averages sometimes. But that's more of a topic for personality or a class that looks at Likert type items like test and measurement than it is for our class. But I just want to mention that many of the items in psychology that we look at have an ordinal scale of measurement. All right. Next, we have an interval scale of measurement. An interval scale of measurement, okay, is a step above ordinal. All right. We have category distinctions like we do with ordinal and nominal. We have rankings that we know a higher number is better than a lower number. And an additional thing that we get is the intervals are consistent. A difference between 5 and 10 is the same as a difference between 10 and 15. That's 5 units difference in both situations, and those 5 units difference are consistent across an interval scale. A good example of this is degrees Celsius. All right, the energy taken to move a liter of water from 0 degrees Celsius to 5 degrees Celsius is the same amount of energy that takes it to move it from 5 degrees Celsius to 10 degrees Celsius. That interval is consistent here for degrees Celsius. Interval scale of measurement, the intervals have to be consistent. All right, how about the year? All right, let's say the difference between 2000 and 2005 and 2005 and 2010. That's 5 years difference. The amount of time that elapses between 2000 and 2005 is the same amount of time that elapses between 2005 and 2010. Your credit score is another good example of this, and shoe size is a good example of this. So the amount of space difference between a size 10 and a size 12 in shoe is the same as a size 8 and a size 10 in shoe sizes. All right, what does an interval scale not have then? An interval scale does not have a true 0. All right, does not have a true 0. It does not have a meaningful 0 in this regard. The 0 is arbitrary. It was just selected by a scientist or by a historian or something, and we say this year is what we're going to call 0. The date in which we call 0 was picked out by theologians and historians. It wasn't picked out because it was the absolute beginning of time. Okay, that would be a true zero in that regard. All right, 0 degrees Celsius is the degree that water freezes. It's not absolute zero, where all electrons, protons, everything subatomic just stops moving. All right. Okay, all molecular energy ceases to be. That would be true zero. 0 degrees Celsius is not that. All right. There's no size 0 shoe. Okay, even a shoe size 1 is a certain length. All right. So interval scales of measurement do not have a true and meaningful zero. You will not see interval scales of measurements that often in psychology. All right. Typically, things go from ordinal and jump from ordinal to what's above interval scales of measurement, which are ratio scales of measurement. Okay, ratio scales of measurement. That reminds me, I need to fix my animations. I need to do that. I apparently did not get those right, but that doesn't really matter that much. I can put everything on the screen at the same time. Ratio scales of measurement. This is a step above interval scale of measurement. What it has that the interval scale does not have is a true, meaningful zero. Zero means, for instance, with temperature in Kelvin, 0 means absolute zero, where all molecular energy is 0. All right. For an interval scale of measurement, the difference between 20 degrees, let's say Fahrenheit, and 40 degrees Fahrenheit, does that mean that when we're at 40 degrees Fahrenheit, that it's twice as hot as that of 20 degrees? No, that's not what it means. Okay, because the zero is not meaningful. However, if we have things in Kelvin, we can do that. Okay, if we're looking at 50 degrees Kelvin and 100 degrees Kelvin, 100 degrees Kelvin is twice as much energy as that's 50 degrees of Kelvin. And that's why Kelvin is an important way of looking at temperature, especially if we're in physics or we're in chemistry. Okay, but you guys don't care about that. You haven't thought about Kelvin for quite some time. What do you care about? How about something like the age of somebody? 0 is meaningful. Okay, 0 is when you were born. Okay, how about weight of something? Again, that's 0. If you weigh 0 pounds, that's something that is weightless. Let's say we're looking at reaction time. Something that takes 40 seconds takes double the amount of time that something takes 20 seconds for. So ratios for a ratio scale of measurement, like what I was talking about, double the amount and so forth, they make sense, but only for ratio scales of measurement. There's plenty of things in psychology that have a ratio scale of measurement, but typically we're in disciplines like neuroscience or cognitive psychology when we're looking at a ratio scale of measurement. Typically we're in things like personality and social psychology when we're looking at like an ordinal scale of measurement. It's not a hard and fast, well, that isn't 100% accurate, but it's kind of a quick and easy rule of thumb to do. Okay, the more nuts and bolts the discipline of psychology is, the more likely we are to have a ratio scale of measurement. All right, so let's do a little bit of review here. I'm going to ask you a question or give you a dependent variable about cookies, and you're going to tell me what the scale of measurement is. This would be much more fun to do in class than it would be me lecturing, but you know, those are the times. How about the ranking of your favorite cookies? Okay, Oreos number 1, Nutter Butters number 2, Chips Ahoy number 3. What kind of scale of measurement is this? Anytime we're doing rankings, we're looking at an ordinal scale of measurement. 1, you like Oreos better than you like Nutter Butters, but we can't tell if the interval between Nutter Butters and Oreos is the same amount as the interval between Nutter Butters and Chips Ahoy. How about the number of cookies eaten? All right, the interval's consistent here. All right, the difference between 3 and 6 cookies eaten is the same as the difference between 6 and 9 cookies eaten. So we're either dealing with an interval or a ratio scale. Is 0 cookies eaten meaningful? And the answer is yes, it is meaningful. So we can calculate ratios. So eating 6 cookies is twice as many cookies as someone that eats 3 cookies. So we have a ratio scale of measurement. How about the type of cookie? So oatmeal raisins, we're going to just randomly label as a 1. We're going to label, why is it taking me a while? Chocolate chip cookies as a 2, and peanut butter cookies as a 3. I don't know, I was blanking out on cookie names. But if we did something like this just for category distinctions, we are looking at a nominal scale of measurement. All right. Some of these names of scale of measurements give you what's important about them. So ordinal, the ordering matters. Okay, the order is the big component that switches between a nominal and ordinal. Nomen in Latin means name. So nominal scale of measurement, we just have a name difference between categories. We don't have a ranking difference between categories. All right, how about temperature of cookies, again in degrees Fahrenheit? This would be an interval scale of measurement because 0 is not meaningful for Fahrenheit. Okay, 1 second. All right, I'm back. So this is an interval scale of measurement. Here is something that gives you examples of nominal, ordinal, interval, ratio. And also, when we get to each step, we gain some more information about the variable and about the numbers, the distinction. So this is just a little thing to help you study. Excuse me. We're going to talk a lot more about this in the future, especially when we get to descriptive statistics and frequency distributions. But what scale of measurement we have is going to help dictate's a strong word, to suggest which statistics we could use. All right. Like I say, taking the average of the football jersey numbers for a football team is not meaningful. The mean doesn't make any sense. So we're not going to calculate a mean for a nominal scale of measurement. If we want to gain any interesting information, we might look at something like the mode. Okay. If we have, for instance, we are coding males as 0 and females as 1, calculating the average of those numbers doesn't really help us out that much. But letting us know that there's more females in the experiment than males, that is going to tell us something. So mode is going to be useful for a nominal scale of measurement, but the average is not really going to help us that much. For ordinal scales of measurement, we're going to get to this a little bit later. Means, we have to be cautious in how we interpret the mean in the ordinal scale of measurement because the intervals are not consistent. So a median is a better measure of central tendency if we have an ordinal scale of measurement. How we can manipulate our data, if we can add numbers to it, if we can divide the data by certain numbers and still come to the same conclusions, we can do that many times with interval and ratio scales of measurement, but we can't do that with ordinal scales of measurement. More about this later on. Also, a couple of things with this last slide. One is interval variables and ratio variables have many similarities to one another. The only difference is that true 0. So sometimes in computer programs, they're going to be lumped together. Sometimes we might use the term scale variable. If we say scale variable, we're referring to both interval and ratio variables. So SPSS, for instance, you'll see nominal, you'll see ordinal, and then you'll see scale. Scale just means interval and ratio at the same time. We can see a relationship between discrete and continuous variables and the other scales of measurement here. So for instance, nominal variables can only be discrete. Okay, they can only be discrete. Ordinal variables, again, can only be discrete. Interval and ratio variables are many times continuous. They are sometimes discrete, but many times they are continuous. They could be both. Okay, but most of the time you'll see a ratio scale of measurement. We're talking about a continuous a continuous variable. Okay. All right, that's it for the day. Hope you guys are doing well, and I will talk with you later. Thank you, and bye-bye.